I'm Joyce Hornady. You might say accuracy is my business. I make bullets.
You are listening to the Hornady Podcast.
Thanks for joining us and enjoy the show.
Hello, everybody. Welcome back to another episode of the Hornady Podcast. As always, I'm your host, Seth. Thanks for joining us. We've got a really great episode for you today. Now, if you remember back, we started a study of ballistics, and we covered the topic of the history of ballistic study, and then we got into what is a Doppler radar. Now, before we advance that into the hardcore external ballistics and what a BC is and what a drag coefficient is and how our forward-off works and all of that, I want to deep dive into what are we up against? What happens from the moment you pull the trigger until that bullet uncorks from the barrel, what a lot would call internal ballistics. And to get the best information possible, I have the brightest minds here at Hornady, arguably. To my left, project engineer Miles Neville, and then across the table, senior ballistician Jayden Quinlan and ballistic engineering technician Jacob Morrow. Guys, thanks for carving out some time to school me up here.
You bet.
Glad to be here.
Our pleasure.
So, like I mentioned in that intro, there's a whole bunch of weeds that you can get really deep into in all topics ballistics, and external ballistics, seems to get the most talked about, probably because it's the one people most care about and is more applicable to them hitting the targets that they want to. And I think one of the fields of ballistics that doesn't get talked about much because largely nobody knows this stuff. There's, we have the ability with the piezoelectric pressure reading system to look at pressure curves and lock time and all of these things that nobody else really has access to. So I feel like it's a good responsibility of ours to propagate some good information that maybe not a lot of people quite know, or if they do know, they don't understand it and its relationship to that bullet getting out of the barrel. So let's start way at the beginning. You're laying down, throw the bolt closed, and you're squeezing the trigger nice and slow. The sear breaks. What happens at that firing event? Where does things start?
Well, it starts with the striker or firing pin impacting the primer itself. So the primer obviously is in the back of the cartridge case, sitting in the primer pocket of the case, and inside that primer, there's a primer cup, right? We've all heard that term. So it's kind of like a little bowl, and then inside of that is an anvil, which you could think of as like a three-legged stool.
Yep.
And kind of mixed between. So it's like that cup. That cup is, if you had the stool, you think of a three-legged stool. If you took a cup, turned it upside down, and set it on top of the stool, that's kind of how that relationship sits inside of a primer. And all mixed up in there, within that cup and all around the anvil is priming compound. And so the priming compound is really sensitive to shock or heat, but the purpose of the primer is to be essentially shocked into working, right? Okay. So what happens is the firing pin or striker pushes itself into the cup, and it pinches between the cup and the anvil that compound that's in there. And when you pinch it, it's very sensitive, and that causes it to ignite, essentially.
Okay. So that priming compound, very sensitive, obviously. Now, that's explosive material, not flammable. That's explosive material. Mm-hmm. Now, if you push on it really, really slow, is it sensitive like that, or do you have to pop it?
Yes. If it's in its raw state, it's extremely sensitive stuff. It's hit or miss in a firearm. Yeah. Okay. Usually in a firearm, you have to give it a good whack.
You have to strike it pretty hard. So if you have a really slow firing pin push.
Yeah. If you have gunk in your firing pin channel or whatever in the gun, and it slows it down enough, you can keep it from reliably igniting primers.
Okay. So is there a set standard on how far you need to push that firing pin into the primer to get it to detonate? Is there a standard in that, or?
Yeah.
There's energy.
Yeah.
Energy standard.
Excuse me. There's a standard for both the seating depth of the primer, like how deep the primer is.
Okay.
Which will probably make more sense here in a minute when we get to like the headspace part of things. And then there's also a firing pin protrusion spec as well. So the firing pin protrusion would be like how far does the firing pin stick out of the bolt face when it's in its furthest forward position.
Okay.
Yeah, there's specs because you have to those both have to be in a controlled manner for it to work.
Yeah,
right?
Otherwise you'd be blasting through things or barely touching it.
Yeah, we got to know that the gun guys are going to have X amount of firing pin protrusion so that when we set our primers and ammo, that those two things are going to work and actually go off.
Okay, that makes sense. So firing pin hits the primer. We learned about the basic construction of a primer. Now that stuff is explosive, so you get this controlled explosion of the primer inside the primer pocket.
Yeah, well, then maybe before that, there's different kinds of primers. So while we're on the primer, you want to talk about that stuff?
Yeah, so people who reload, they're going to notice, like, obviously there's small pistol, there's small rifle, large rifle, magnum rifle. All those primers are designed with a purpose, to reliably ignite the powder in the cartridge. So if you use a pistol primer in like a 300 PRC, that isn't going to give enough flash to reliably ignite the cartridge. You might get issues like hang fire. So that's why you'd move to a magnum primer, because that's going to have a little bit more compound, a little bit more energy to ignite that tall powder column to make sure you don't get hang fires.
Okay.
There's kind of more disparity on the rifle in the rifle application than the handgun or pistol primer application, because you think of, like, when you think of the application of the primer, you have to think about the propellant too, because that's the primer's job, is to interact with the propellant and get it lit and going. So within pistol cartridges, your charge weights of your propellant may be anywhere from a grain-ish on the really small stuff, like a 25 auto, a grain and change maybe, up to
500 Smith & Wesson.
Yeah,
40, 50 grains. For the really big.
So that span compared to the span that's in the rifle realm, which would be anywhere from like the teens, right?
Yep.
Somewhere between 10 to 20,
yep,
up to north of 100.
Yeah.
And so that's a big gap, right? So essentially the differences in pistol primers are not as huge as the differences in rifle primers when you talk about the sizes and the magnums or the standards and all that kind of stuff.
And a lot of that stems from the amount of the priming compound, that cake that's in there. Is just the amount change, or is there different in chemistry? Likely.
It's a little bit of both.
Okay.
Yeah.
So different primers for different jobs, and firing pin strikes it. We're lighting it up.
Yep. So
what's happening?
So primer's active now. That little explosion occurs, and in that primer pocket that's in the back of the cartridge case, there's a hole that goes completely through that. So if you looked at look down inside of a fired or an unfired cartridge case, you can see that it's kind of solid in the bottom, and there's a little tiny hole down in the center. Yep. That's your flash hole.
Okay.
So the purpose of that hole is to allow that that compound of the primer that is now exploding or burning or creating spark, however you want to think of it, a place to get through the cartridge case into call it the propellant bed, or the body of the case,
in a very concentrated manner, because those flash holes are not very big.
Right, they're pretty small.
Okay.
Yeah. But the other really important thing that happens in that cycle that many people aren't aware of is that when that primer goes off, it's generating pressure when it does that. And it generates enough pressure that in some circumstances, the bullet will start to move in the cartridge case before the powder is ever even burning.
Oh, wow.
That doesn't always happen. It can happen. It depends on a whole bunch of things, mainly the kind of the oomph or the power of the primer and the volume of the cartridge case and how much propellant is in it and all that kind of stuff.
Neck tension, probably.
Yeah, neck tension. Yeah, all those things. So it can or it can't happen, both of those circumstances, depending on the specifics. But as that pressure in the primer is building, it actually backs itself out of the primer pocket, which a lot of people don't realize, because what they see is a loaded round of ammunition, and the primer is, seated into the primer pocket, and it's a flush or a little bit below. And then they fire the cartridge and they extract and eject that out of the firearm, and they see that the primer is kind of in the same spot that it was when they shot it, or it looks that way. So what's interesting is that the primer will generate enough pressure that it backs itself out of the primer pocket until it hits the breech face.
Wow.
And then it stops there. So in that first ignition cycle, it's like the primer's trying to detach itself. It's trying to shoot itself out of the back.
It's like
of
a
the
rocket.
cartridge.
You got an explosion going one way, it's going to find the path of least resistance, and it's going to back itself out of the case. Okay, that makes total sense.
Yep.
Didn't quite appreciate that. So it's slammed up against the breech face, and in some cases you said the bullet moves. Now, that's theoretical, but you guys can actually see this when you look at a pressure curve. You can actually see that event early on in the pressure cycle in the curves that the software generates.
Right.
What's that look like? A little spike in the pressure, or how does that?
Well, pressure is directly tied to volume. So the easy way to think about that is, like you have a air compressor and your little gauge is reading that you have 30 pounds PSI of pressure in that tank. And if you take your little air hose nozzle and you let the air out, you're taking the air from that fixed volume that is the amount of air that's in there equals 30 PSI, and you're letting it out into the volume of the atmosphere, right? A much bigger volume. What happens to the pressure?
Yeah.
Pressure drops, right?
Okay.
So pressure and volume are tied together, and you have to kind of keep that in your mind as you go through these next stages of the cycle. So when the bullet starts to move, now you're starting to change the volume that's behind the bullet. So it's kind of a static system before the bullet starts to move, because the volume of the cartridge case
is the same.
Yeah,
There it is.
It's defined by the dimensions of the brass, and that really doesn't change in this part of it. So as the bullet starts to move, the volume starts to increase. When the volume starts to increase, if you're not continuing to generate more gas or pressure from the primer, then the pressure will drop because the volume's increasing. And so that's how you can see it.
Okay.
You'll see pressure will start to go up, and then it will start to drop. And what that indicates is that the volume was increasing, which caused the pressure drop.
Yeah.
I guess it's not that you're not generating more pressure. It's just that your volume is outrunning the pressure build.
Yeah.
The gas. You're converting solid to gas, and so the volume of that powder expands dramatically. And yeah, if your volume expansion outruns that pressure generation, that's what you see.
Yep.
Okay.
Yep.
So bullet maybe does, maybe doesn't lunge forward. The firing pin backs out slightly from the case. We're shooting this flame through the flash hole, and we're lighting up the propellant bed. Now, we could spend a long time talking about propellant as a whole, and I think that's another topic that a lot of people maybe know some basics on, but not very in-depth. But there are different types of powder, and they do ignite slightly differently. So what's that look like with the flash hole coming through into the powder bed?
So yeah, I think you have to address the different types of powder before you can start talking about how powders burn. So there's a couple main types of powder. You have stick, ball, and flake is what we're probably most familiar with in reloading or hand loading or even ammunition production. And those are just different geometries, right?
Okay.
And then within those, you have categories of kind of the chemical makeup. So there's single base powder and double base powder. There are some triple base powders out there. They're generally not used for small caliber stuff. So 20 millimeter and below essentially is that definition. Single base powders are nitrocellulose, and they might have, that's their main component. And
Okay.
they may have some other chemicals involved with them. Double base powders would be nitrocellulose and nitroglycerin. So they add nitroglycerin in to up the energy content of the powder. Essentially, it can give you more velocity for the same level of pressure. And then the triple base stuff, that's not applicable enough to even go into. But within those two, so you have your shape can control the burn. So think of flake powder like a piece of paper. Think of ball powder like kind of a bunch of pieces of paper that you wadded up into a ball. And then think of stick powder or extruded powder as like a stick. Like a
piece of paper that you rolled up into a tube.
And so if you threw all three of those things into a campfire, they would all burn at different rates, right? And mainly that's controlled by the surface area that they have.
Okay.
It's like the piece of paper, there's just a flat piece of paper has essentially all of its surface area exposed and able to burn at that instant in time. If you take that piece of paper and you wad it up and you throw it in, only the outside of that wad of paper is exposed. And so as that burns, it burns through into the inner surface area. So it slows the burn rate down. And then the stick is obviously the other extreme end of that. And you can have like perforations, like a lot of extruded powder, there'll be little holes through it so that you can increase the surface area that's exposed so you can control the burn burn rate that way. So that's kind of like a small crash course in what kind of propellants there are.
Okay. Yeah, and just by explaining that with the piece of paper, that's a great analogy. Because, you toss a single piece of printer paper into a fire, and it lights up real quick. And if you smash that into a little ball, it takes much longer to burn all the way through. And, again, that's a pretty high-level explanation, but a good explanation nonetheless. And I'm sure there are different desirable features of each for certain types of loading. Generally, I know a lot of us long-range guys and precision guys shooting extruded powder. They seem to be really temperature stable. Usually they're single-based. Is there anything to that you could explain, the double-base versus single-base temperature sensitivity?
Sure. Maybe a little, something you said spurred something in my mind. A lot of the powder application comes down to how much you can fit within the cartridge case too, right?
Oh, volume.
Your volume's fixed. That's out of your control. So a lot of times you'll see ball powder used in instances where capacity is low. It's like you almost never see an extruded powder used in a pistol application.
Right.
But you have such limited space. That cartridge case is really small, and the bullet's stuck pretty far down in there in most of the pistol cartridges. So ball powder works great there, or even flake powder. There's flake powder used there too. But that plays into the application of it. But as far as like temperature sensitivity or how the powder reacts, you're absolutely right. So generally a single-based powder is the least sensitive to changes, whether that's changes in the volume, like you were talking about, Miles. So cartridge case to cartridge case, 6.5 Grendel to 6.5 Creedmoor to 6.5 PRC, you would probably see less change in performance with an extruded powder used in all those circumstances than you would like a ball powder that has nitroglycerin in it to up the energy content. So they're more sensitive, but one of those sensitivities is temperature. So if you're shooting your ammo in really cold in the winter or hot in the summer, you're going to see more changes in your velocity and pressure with that nitroglycerin double-based powder. Because it has the higher energy content, it's more sensitive.
Okay. So now we've got the firing pin hitting the primer, backing out the primer, shooting the flame through the flash hole. We learned about some propellant, so we light up that propellant. What's that next step in this firing sequence?
As the propellant starts to burn, as Miles said, what you're doing is you're changing from a solid state of energy into a gas. So that energy exchange is happening, and it's happening in a way where there's pressure being built in the system. If the bullet started to move just because of the primer, it's going to start moving faster. Now,
Sure.
If it wasn't moving yet because of the primer, it's going to start moving now. That powder is generating enough pressure to start moving the bullet out of the cartridge case.
Okay.
And the resistance of the bullet to moving is the grip of the cartridge case onto the bullet. So if it's a bottleneck rifle case, it's that neck area of the case. That's what's gripping the bullet and holding it in. So once the pressure generated by the propellant burning, going from a solid to a gas, once enough pressure is generated to overcome the forces of the case holding the bullet starts to move. Now, Once bullet starts to move, now volume is increasing behind the bullet. So what you'll see is pressure should be dropping off. If your rate of energy transfer from that solid to a gas was constant, you would see the pressure drop off. But what happens is they manufacture the powder with that in mind, essentially, hey, this volume's going to start to change because the bullet's now moving. So we need to up the speed of the powder so that we're generating more pressure than the volume is increasing behind the bullet.
Right.
And so that's kind of an explanation of burn rate.
Yeah, why some powders are slower or faster burning than others.
Mm-hmm.
Okay.
And the burn of powder itself is dependent on a couple things, and one of them is pressure. And so as the pressure goes up, the burn rate will go up as well.
The faster it starts to burn.
Yeah, faster, the higher the pressure is, the faster it burns. And those, you could just repeat those two words for infinity, I mean, that's kind of how you reach your max pressure.
Oh, wow.
That's why it's such a big deal when you have a bore obstruction, because then your volume doesn't expand at all or at the rate that it's supposed to.
Okay.
And then your pressure just
and so
through the roof.
more pressure, more burn speed, more pressure, more burn speed.
Right.
And then
until you run out of energy is what happens.
Yep. Okay. Now that rate of more pressure, faster burn rate, more pressure, faster burn rate, is that what is referred to as progressive burning or progressivity?
No, progressivity would probably be more tied to the volume increase.
Okay.
So a very progressive powder burns in a way that at the rate that the volume is increasing, the gas generation from the powder is just a little bit more than that. It's not a perfect match, because if you had a 1-to-1 match of pressure generation to volume increase, that it would stay static, right? There would be no pressure increase really at all. But when those two are just kind of going neck and neck, just at the same time, that's when you would
Okay.
kind of use progressive is the term.
Awesome. So we got that lighting up, the bullet's starting to move. Now that pressure is getting robbed a little bit because the case is expanding in the chamber, correct?
Yeah.
Once you get to a certain pressure built up inside there in the case, then yeah, you're obturating the case and it seals. It's a gas seal basically is what you're looking for. Ideally, if you don't get it, then you have problems. But yeah, you want the case to seal against the chamber wall, and that keeps all of the gas going down the bore and none of it escaping around.
Mm-hmm.
And so if you have like extreme examples of that, if you guys, people at home have ever seen it, the gas will actually get around the mouth and collapse the case back in on itself.
And that would be because of either a low charge or a too slow burning propellant that
Right.
it just didn't
Yep.
seal
Or
that
yeah,
case
too
off.
much room. Yeah, combination of too much room, too little volume at the right timing, and then pressure increases. Or I'm sorry, too little pressure, and then yeah, just the timing of it all is a little bit out of whack.
Awesome. So we're sealed up against the chamber now. The powder's burning, propelling the bullet into free bore.
Yep.
And the free bore is the unrifled portion of the barrel, and it should pass through there without touching anything, presumably. Or how does that handoff go?
Yeah, it's kind of bouncing off the walls a little bit. You could probably think of it as. I mean,
Okay.
it's tough though because you can't like go sit inside the chamber and watch the bullet go by and be like, "Yep, that one didn't touch anything." Oh,
Okay.
that one was bouncing all over the place. You know,
Yeah.
you can't really do that. So it's hard to theoretically you could say that the bullet is constrained from moving, say, left, right, up, and down from our perspective behind the rifle as the shooter by that free bore dimension. So
Okay.
the tighter that free bore is, the less the bullet is able to just kind of do whatever
Yeah,
and bounce
pinball
around
in there.
Right.
Okay. So a good example of that would be 300 Win Mag versus 300 PRC.
Mm-hmm.
When you look at free bore. What's the free bore on a 300 Win Mag? I don't remember it exactly, but it's big.
314, 15?
Yeah, I think it's
Yeah.
three.
Or am I thinking 30-30?
No, it can be up to like 315, 316 on the max. So like the SAMI definition, or the SAMI dimensions generally call out the minimums, and then you can be plus 2,000ths on diameter. And yeah, I think those are. Yeah, it's big.
Yeah,
and
so
and
let's
that
say
comes
the-
from that old design.
Yeah. So it's 308 thousandths bullet, 0.308, and then you have a free bore that's 315. Now on the 300 PRC side, you got a bullet that's still 308, but the free bore's 308.5 or
Yeah.
308.8. So we've got
Amen.
0.8 of a thousandths divided by 2, essentially. That's how much room it has. So it's held straight.
Mhm.
And so if it's held straight through the free bore, it will enter the rifling straight. And I've got to assume that handoff is hypercritical for accuracy.
Yes, absolutely.
That's what, yeah, I think like when you hear people talk about jump sensitivity when they're, seating bullets to different depths, I think a tight free bore, relatively tight free bore, not like constrictive, but like not a ton of room to wiggle, that definitely helps in terms of sensitivity for accuracy.
Okay.
When you've got, a little bit more of less of a big open funnel and more of just a straight shot for the bullet to go through.
Wow.
You
So
see that pretty commonly, like bench rest shooters. They'll
Mhm.
get custom reamers made, so that way they can control what they want for that free bore.
that
so-
makes sense. And so it's possible to say that bullet jump sensitivity may not be so much dependent on the bullet, but the chambers that they're being fired in.
Both for
Both,
sure.
yeah.
Because the bullet's contribution to it is, you could think of it as like the wheelbase, like or bearing surface. I mean, its technical term is borelay length. The borelay length is slightly longer than the bearing surface because it's defined by the bore diameter, not the groove diameter. But that left aside, a bullet with a really short bearing surface, that thing can tip a lot.
Okay.
Versus one that's really, really long, like a round nose bullet.
Yeah.
That thing can't really tip much because it's essentially full diameter for such a long distance that it can't tip. So the bullet does contribute to it.
Bullet contributes for sure, OJ profile and
Yeah.
and then probably more specifically bearing surface or borelay length that you're talking about. But then if you're shooting it through like you mentioned, Miles, not a constrictive diameter, but a relatively tight diameter on the free bore, that'll hand that bullet into the rifling straighter.
Yep.
And what happens when it enters crooked, like say in a 300 Win Mag, which is a notoriously hard to get to shoot cartridge in a factory chambered rifle? That's why people have the the 1997 match reamer and the different tactical reamers that control that. What do you call that handoff, and what happens when you enter crooked?
Well, going from the free bore, there's an angled step into the rifling.
Okay.
So
and you can see that on the SAMI drawings.
Mm-hmm.
Yep.
Yeah. Or like if you use a bore scope or get on the internet and search for like bore scope images or whatever, there's probably videos of it too with bore scope recordings. But you can see that spot where the rifling, it's like a ramp to the full rifling.
Okay.
And so that's your lead, is the
lead angle.
Yeah,
Yep.
That's the technical term for that. So as the bullet is entering, it's transitioning from free bore into the lead, that angled portion of the rifling where it reaches full rifling. If the bullet is tipped or crooked at that point, bullet's pretty soft compared to a steel barrel, right? Like you could take a bullet and put it on a table and just take a little hammer and dent it, right? You do the same thing to your barrel and your barrel doesn't care. So the barrel's way harder. So if that bullet is crooked, when it tries to get engraved into that rifling through the lead, it's going to stay crooked. The bullet's going to give. It's not going to straighten itself back out. It's not hard enough.
So if you don't enter the rifling at a consistent angle every time, you're not going to have consistent accuracy.
Correct. Yeah.
So that's why free bore diameter is such a critical part of accuracy in a nutshell. And there's no secret to when we design a cartridge, we take that into heavy consideration. And when we make a SAMI spec chamber reamer, we set those dimensions so that you can buy the really affordable rifle or the really expensive rifle that was custom built, and they're all going to lend themselves to being really forgivingly accurate.
Mm-hmm.
And that a lot of that shares itself there. So before we get too far of the bullet down the barrel, there's some other things to consider, and one of which is headspace, which we should probably talk about. Yeah.
So we should back that up to when we were talking about the primer, the firing pin or the striker, denting or making its way into the primer cup. That doesn't happen because the cartridge has to have play or room within the chamber. Otherwise, you wouldn't be able to chamber it if there was dirt or grit or whatever it wouldn't fit in the system, right? Yeah. So there's a little bit, the cartridge is a little bit undersized to the chamber so that it can make sure and fit in there. So what happens when that firing pin or striker hits it is it pushes the cartridge forward until something stops it. And what stops it is the headspace mechanism. And you have rimmed cartridge.
30-30.
Like a 30-30 is a great one. You have bottleneck rimless designs. So that's the majority.
Yeah,
right?
308, 65 Creedmoor, 243.
Yep. And then you have case mouth headspace, which would be most of your pistol cartridges.
9mm
like
Luger.
So they actually,
belts.
Yeah, belted magnums. Yeah, absolutely.
300 Win Mag.
Yep. So each of those things is the mechanism used to stop the cartridge from moving forward.
Okay.
In the chamber. And so that technically is what happens before the firing pin or striker can punch into the primer cup and cause it to go off. So we kind of left that one behind.
Left that out. So the firing pin hits the back, pushes that case forward,
mm-hmm.
and it's kind of absorbing the blow,
mm-hmm.
which is probably why it's critical that it's a hard, fast strike of the firing pin, because it's going to absorb a little bit of that to push the cartridge forward until the headspace mechanism hits a hard stopping point, and then the rest of the firing pin protrusion and force is used to detonate the primer.
Another consideration with that is if your headspace is too long, say like 10 or 20 thou over the SAMI max spec, your firing pin could hit that primer and it push the case forward and it could not detonate.
Yeah, you get a light strike.
Yep.
You'd hit it as hard as you want to, and it's just going to move forward.
Mm-hmm.
There's some cases where the extractor could hold that rim hard enough that when the primer strikes it, or the firing pin strikes the primer, it still ignites the primer, but if it doesn't, then it's just in free space.
You don't want to rely on your extractor to hold your case.
So that's not a good situation.
That would be a circumstance where your headspace is too short. So the
cartridge
cartridge case would go so far into the chamber that the firing pin or striker could never get to it,
mm-hmm.
right?
Yeah.
Because the headspace is so short that it moves so far forward. But like what Jacob's describing is that extractor is holding on to the rim of the case, and if it has a good enough grip and can hold it rigidly enough, the striker or firing pin can still detonate the primer there, even though the cartridge isn't technically headspaced at all.
Wow.
Because it's not stopping off its designed mechanism to stop it.
Just to clarify, you're talking headspace of the cartridge, not
correct.
Yeah, headspace of the chamber would then be too long. Vice
yes,
versa.
Yeah. Short headspaced cartridge, or vice versa, long headspace chamber.
And it would probably be advisable for anybody that's listening and anybody that's really wanting to learn about this stuff, to just take a few minutes, and if you haven't done so already, go to SAAMI.org, SAAMI.org, and you can look at all of the approved chamber drawings, and you can see the chamber drawings and their dimensions and their tolerances, and then right above that, you'll find cartridge chamber drawings and dimensions, and you can see what tolerances they have so that the cartridge can always fit in the chamber.
Yep.
You can learn a lot from that. And if you haven't done so, and you're a passionate reloader or a shooter, it'd be worthwhile to just go out there and familiarize yourself with what those are.
Yeah. Because that's a good point, I think, because that's set up so that, because the other side of that is tight headspace where things interfere. And if you look at the SAAMI drawings, you'll see that usually they've got it almost 1-to-1 fit, so that the max cartridge and the minimum chamber are a 1-to-1 fit, so that they basically fit with almost interference, but no interference. And then the cartridge can be shorter on headspace, and then the chamber can be longer on headspace within those allowable tolerances to give you, a net. Usually it's about a 10,000th window.
Okay. So now we're back. The bullet is handed off into the rifling through the free bore, through the lead, and we talked about lead angle and getting engraved in the rifling straight. And if it doesn't engrave straight, that never comes back. If it engraves crooked to some degree, it will come out crooked. So what happens? What are we dealing with from the moment it engraves in the rifling? Obviously, there's force there till, as it travels down the bore. What's going on?
Well, I think we should step back one step back to free bore right before it engraves, because there's something really important there for people to understand, and that's the free bore length.
Oh yeah.
So a lot of times, what you'll see guys do is there's a term, throating your chamber out, where you go in and you make the free bore longer, or you can get a custom reamer made that has a shorter free bore if you're going to shoot a certain bullet and you want a certain amount of bullet jump or whatever. The important thing to think of with free bore is that's the free run of the bullet, right? After the bullet comes out of the case neck, there's nothing holding the bullet back anymore. It's just free to move forward, and it's free to just jump through that free bore section until it hits the resistance of the rifling. That free movement means that you're getting a very rapid increase in volume, right? Because there's nothing holding the bullet back. It's just flying forward.
Yep. So that'll drop the pressure if it's super long.
Mm-hmm. So the longer your free bore gets, the more you're going to drop the pressure of that early stage of propellant burn, because the volume can just increase so quickly. So if you do the opposite of that, you run a really short free bore, then the opposite of that occurs. You're not increasing much volume before the bullet hits the resistance of the rifling, and you'll get higher pressure. So those out there that are either wildcatting or are just going to have a custom reamer made that is a modification off of a standardized cartridge, I'm going to get a 6 Creedmoor, but I want the free bore to be 50 thousandths shorter than what is standard. Understand that what happens when you do that is you're going to generate higher pressure with all other things equal. If you do the opposite of that and you run a longer free bore, you're going to drop pressure with all things being equal.
Wow. So that's why it's hypercritical for reloaders, and anybody who shoots a rifle or a firearm, to understand that your firearm can really make the difference between high pressure or low pressure. If you're experiencing signs of high pressure, it might not be, everything could be great. It's just that specific chamber, the way it was cut, with what reamer it was cut, could be the cause of your high pressure, and needs to be appreciated if you're hand loading, if you're wildcatting, if you're getting custom reamers made, that there are definitely implications.
Even reamer wear can tie into that, because you can send your reamers in to get resharpened, but every time you do that, those dimensions are getting smaller by a really small amount.
Yep. Well, and think about the OEM guys, the big rifle manufacturers. From a cost standpoint, they probably want to get as many guns chambered as they possibly can. And you start with a max spec reamer and you chamber a bunch of guns and then get it sharpened, and now it's maybe a little smaller. And you might end up with one that's really, really tight, even if it's on the bottom end of the spec, but still in spec. That's a big window, and that could definitely affect some things.
Yep. Yeah, I guess another thing we should talk about. So while that pressure is building up in that early firing, your case will obturate and seal against the chamber. And then there's like a classic internet debate about what's better, to have a rough chamber wall or a smooth chamber wall. I don't know, one saves your brass, the other one puts less bolt thrust on the bolt lugs, right? But either way, to some extent, your chamber or your brass is going to expand, grab the chamber walls, and then in the web of the case, you're going to have a little bit of unsupported case, or where the web is thick enough that the brass won't expand all the way. And that's going to, so we talked at the beginning, the primer backs out, it hits the breech face, hits the bolt face. Well, then once that pressure ramps up, your chamber, your brass expands, fills the chamber, and then the back end of the case is going to actually expand and stretch backwards. And then that's where you get, so you see your fired cartridge case has a primer flush with the back of the case.
It backs into it.
And that's because if you get a build up enough pressure, then the case actually stretches and the head of the case will slide back into the bolt face.
Okay. And then that ties into headspace. If you've got extra headspace cut into your chamber, that cartridge can go forward and stretch backward.
Right.
And now you're starting to get a separation ring.
And that's, you can measure before and after firing with like a comparator tool, and see what your headspace growth is. And then if you don't have a high enough pressure to cause that to stretch, what you'll see is if you have excessive headspace, you'll see the primer stay backed out of the case.
Wow.
So you'll eject a case out and you'll see that the primer is still sticking out of the case, however, whatever that distance is.
Yeah, if anybody out there is a reloader or a hand loader and they want to prove that to themselves, just chamber a fired case. Don't put powder or bullet in it. Just a primed case. Chamber it in your rifle and shoot it, and then pull it out and look at the primer, and the primer will be sticking out of the case.
Yeah.
Then in that circumstance, you didn't generate enough pressure to do what Miles is talking about, where the brass actually is growing lengthwise and it seats itself back over the primer.
Yep.
And you can see kind of an example of what we're talking about.
And in a bolt action rifle, you could certainly do that experiment. Would not recommend that in a revolver because you'll lock that cylinder up.
Yeah, don't do that in a revolver. Yeah, good point.
So we talked a lot about getting that bullet into the rifling, and now we're at the point where the bullet's going to start, it's engraved, and now it's going to start traveling down the bore. And what kind of event is going on there? Just, I'm guessing, powder rapidly increasing in burn rate.
Yeah, because it takes a lot of force to press that bullet into the rifling.
Sure.
And if you want to see what that's like, and you're a reloader or a hand loader, take a component bullet with obviously unloaded firearm, but try to press that into the muzzle with your finger. It isn't going to happen. There's a lot that's involved there. So that bullet has that free run where it's just flying towards the rifling through the free bore, and then it hits the lead angle and is trying to engrave into the rifling, and the forces go way up. Bullet stops moving forward, essentially. So now your volume's back to kind of a fixed, right? The volume was increasing as the bullet was moving. Now it hits the rifling and it dramatically slows down, if not nearly stops. Powder is still burning, but now volume is fixed. So now you're going to start increasing pressure because powder keeps burning, pressure keeps increasing. Pressure makes powder burn faster, and you go back with those words again and and stack them up. So this is where you're starting towards maximum pressure, is that bullet's getting engraved into the rifling, and you will reach max pressure within those first few inches of the bullet into the rifling.
So it's climbing in a hurry, when that's what starts the acceleration of the bullet, and then you hit that peak pressure, which for most bolt-action rifle cartridges is somewhere in the tunes of 58 to 65,000 pounds, depending on what cartridge you're shooting. SAMI publishes those dimensions. And from a manufacturing standpoint, that's where you guys get to go swimming in the world of powder and pair a very specific burn rate and chemistry to each load to maximize that pressure curve and get all the velocity, and you get the moderate pressures and good accuracy. That's where you get to really play with that kind of stuff, which is fascinating.
Yeah, I don't know if we want to touch on that. I don't know, like with every given cartridge, over your burn rate of powders, and there's burn rate, and then energy density, is that a good term, I guess?
Yeah, sure.
Yeah. So you got the burn rate spectrum, and then each individual powder has its own energy density, and so there's general trends with burn rate that fit certain cartridges, but then within those, there's also that energy density, I guess, if you want to think of it like that, that different powders are more optimized for certain cartridges and bullet combinations as well. That plays into it. But then, so you can achieve the same pressure, but not get the velocity out of it. So if you have too fast of a powder, you'll have a low case fill. You have no problem getting pressure out of that powder, but you'll never get the velocity that you want. And then if you go on the other end of that, you can't get enough powder in there to build up enough pressure. So you'll stuff the case completely full, put a bullet in it, and you'll still hit 40,000 psi max, and there's no way to get more oomph out of it.
So it takes a lot of playing around, and luckily there's been decades worth of ballisticians printing things like our handbook of cartridge reloading that narrow it down for the hand loader. Now on our end, we get the awesome benefit of having a pressure reading system, so we get to see that, and that's how we can tailor the powder for each specific load and each specific cartridge, which is pretty fascinating.
Mm-hmm.
So as the bullet's traveling down the bore, it's just friction and pressure is all we're really working with.
Yeah, you're kind of right in the meat and potatoes of that volume pressure relationship, because now you're dealing with a lot of volume. In the first instances of the ignition cycle, when the bullet's still back in the case neck, that volume's pretty small. By the time the bullet has reached like 2 or 3 inches into the rifling, the volume behind that bullet is way more than it was before.
Sure.
Now this plays into what caliber you're shooting, or what is your bore dimensions.
Mm-hmm.
So if we look at it from the perspective of a 223 and a 338, right? Those are two totally different
diameters. Yeah.
Quite obvious. If you move them the same distance, let's say that from the bullet sitting in the cartridge case, it's moved 3 inches into the rifling, and the chambers are the same length. The rifling and the lead and the freebore are all the same length. Everything's a constant. The amount of volume that is behind the bullet in that 223 is substantially less, even though it's at the same position as, say, this 338 bullet, and that's because the bore volume is bigger. And so that's why you really see, like as a reloader or hand loader, you look at the reloading handbook, and you see so much differences in the like recommended propellants or the powders. You see Varget used here with a 308, but when you go to a 338 Winchester, which is essentially, 338 Federal.
Yep.
The 338 Federal is essentially a 308 necked up to 338. So everything else is the same. You just made it bigger. You see that you have to go to a faster powder. Well, that's kind of counterintuitive, because the bullets are heavier. 338 bullets are heavier in general than 308. So if the bullet's heavier, why would you go to a faster powder? That seems counterintuitive. It's because of that volume. The powder has to burn so much faster because the volume is bigger. So every inch of bullet movement of a 338 is increasing the volume way more than an inch of bullet movement in bore of a 223.
Yeah.
And so that's kind of counterintuitive to people, but it's important to understand.
Yeah, that is important to understand, and that scales up and down to everything. And yeah, when you go larger in diameter with the same cartridge size, yeah, it seems counterintuitive, but it does make absolute sense. Do we want to talk at all about huge cartridge cases in tiny bore diameters? We want to touch on some of the hurdles that creates, and some of the problems that can create. Because we see there's been periods where people are all about hot, nasty speed, and that's cool. And there's still some modern cartridges being designed that really focus on hot, nasty speed as the key driver for external ballistics. And that's just really old school thinking that, we've advanced past that. But there's still some cartridges popular that do that. And, you look back at like the Weatherby cartridges, for example, back in the 50s and 60s. Hot, nasty speed. Let's make a big case. 257 Weatherby, for example, that's a big case. That's a small hole, and that thing is cruising. So what kind of hurdles do what I'm going to call overbore cartridges bring to the table in this study of internal ballistics?
Well, you were just messing with fouling.
Yeah, fouling is a especially large part to that. It's really easy to think about. More powder is going to have more fouling, because most of that powder is getting turned into gas, but then you have like carbon. That's a result of burning that powder. And as that deposits itself in the bore, you're kind of constricting and adding more friction to that bore as that bullet passes through it. So you have to kind of be really careful with your cleaning regimen to make sure you're not going to get any pressure issues by going too long.
Well, and you said carbon. Yeah, when you think about that. So if you had two cases that were the exact same size, like you just mentioned, and one's 25 cal and one's 30 cal, there's more room for carbon to deposit in the 30 cal bore than the 25 cal bore. And if you deposit enough carbon in enough critical areas, maybe your case neck doesn't have enough room to expand to let go of the bullet, or maybe your bullet is engraving in really hard carbon before it's engraving in the rifling, and that can dramatically change your pressure and create some real problems.
Well, just like we talked, how if you move your throat closer and closer, well, you can artificially do that with carbon fouling.
Yeah,
Yeah,
absolutely.
that's what makes a carbon ring, what
Yeah.
people call it. If they have a ring of carbon in their throat, that's essentially shortening your throat. So now that's why you're dealing with higher pressures.
So if you chamber a round and then you pull it out and it has like resistance, just a live round that you never shot, and then you look and there's scratches all the way down the bearing surface, odds are, you got either a super tight chamber if it's clean, but if you've been firing it, 100, 200 rounds, then you probably have carbon in there scratching your bullet up. And so you're starting out where we said we had a non-restrictive, tight fit. You have now a like 1-to-1 fit.
Yeah, or
restrictive.
or
even
none.
more.
It's jammed in there. Okay, so that's definitely an important thing to consider. And on the overbore side, I mean, that's just you have to fill them full a ton of really slow burning powder, and that's generally not a good way to do things for the most part.
Yeah, and then you run into it seems the slower burn rate you go on powder, the fewer options you have to choose from, and you run into issues where you can't fill. There's not an option that appropriately fills that case enough to get good case fill density.
Yeah, delivers optimum.
Right, velocity and pressure, performance. And so then when you get low case fill percentage, you run into issues where you have powder forward, powder rearward, and you get dramatically different
velocity,
pressure and velocity curves out of that if you're shooting uphill, downhill, or your ammo is moving around or however.
Okay. Well, I'm going to probably save this round for when we talk about that bullet uncorking from the muzzle, but there's got to be some truth to, well, if it's really, really slow burning powder and you're chasing that bullet out of the muzzle through a really small bullet diameter or bore diameter, that can't be advantageous to accuracy either. But before we talk about that, where are we at with the bullets traveling down the barrel, the pressure's climbing, and we talked about the volume increase differences. Now that bullet's getting close to the muzzle or at the muzzle. Now what's going on?
So
I got a fun analogy for the pressure and volume relationship.
All right.
Your bullet is a little skinny dude on a teeter-totter, and your pressure is a big fat guy on a teeter-totter. And then, you set them basically when you fire your firing event, the teeter-totter's kind of in the middle, and you let them go, and that pressure starts to accelerate the bullet, and then basically your volume change is moving the pivot point of that teeter-totter towards the fat guy.
Okay.
And so that's the way I like to think of it.
That little guy starts moving real fast.
Yeah, so he starts moving real fast, but then the more you increase the volume, the closer that teeter-totter goes to the fat guy, the less effect that pressure buildup has, and eventually the volume overtakes that pressure growth.
Yeah. So perfect add on to that, because your question, what happens down bore a little bit when you hit max pressure? You hit what Miles just said. You hit the exact match between volume behind the bullet and gas generation of powder. That's where they're at a 1-to-1 is your maximum pressure. What you see from there is the bullet's been hit pretty hard, and he wants to get out of there. So he's going to keep moving even if you don't generate any more gas, which is exactly what happens. You hit max pressure, and by default, if you continue on past max pressure, the pressure starts to drop off. That pressure is dropping off because the bullet keeps on moving, so the volume keeps increasing, but you're not generating enough new gas from the propellant burn to keep upping the pressure. So by default, pressure begins to drop as the bullet continues down bore.
Wow. And how's barrel length play into this? Because it obviously has to.
Yeah, yeah. So that curve is essentially a fixed thing, with all of the dimensions and stuff being a control, right? Same free bore length, same bore and groove diameter, same bore and groove condition, all that stuff is a fixed value, a constant for the sake of this. That gas generation curve or the pressure versus time curve of the powder is what it is. It's not going to vary much if all those things are held as constant. But what happens is, like you said, we'll get to it in later podcasts about what happens when the bullet uncorks from the muzzle, but the amount of pressure that is still in the bore at the point where the bullet uncorks from the muzzle is a major player in dispersion or accuracy. But what happens with barrel length is when you start cutting your barrel back, you're not changing the generation of that pressure curve at all. Like that's a function of those dimensions. And just because you're cutting the barrel back, you're not changing all the dimensions that are still there. And so the pressure at muzzle exit will increase as you cut the barrel shorter and shorter and shorter and shorter.
And you're basically losing that pressure pressure. So it's dropping off as you go longer and longer barrels. So your benefit in velocity as you go longer and longer with barrel length diminishes as you go along, but you still have pressure behind the bullet for time, and that's basically what pushes the bullet faster and faster and faster. And so as you cut your barrel down shorter, you lose muzzle velocity. Basically, you're losing that push versus time that you would have had. You're cutting that away.
It's basic physics. It's force over time. You're shortening the barrel. You're shortening how much time you can apply force.
Yep. Okay, that makes total sense. Now, is there an accuracy component in some instances in shortening the barrel and having higher muzzle exit pressure?
Oh, for sure. Yeah. Generally, what you see is as you cut the barrel back, the bullet is going to uncork from the muzzle with more and more pressure available behind it. And that's not a positive thing for accuracy. Because when the bullet, we're starting to allude into the other one, but I don't think we have to go too far into it.
Right.
When that bullet comes out of the muzzle, when it's still in the muzzle, it's held by it, right? On all around the circumference of it, it's held by the barrel. When it just uncorks from it, it's now free to move in any direction because it's no longer held by anything. So when it uncorks and it's free, and then you smack it on the back end with this giant amount of pressure that's coming out of the muzzle.
Which is traveling faster than the bullet.
Mm-hmm.
Yep.
It's generally not good for accuracy or dispersion.
Okay. And now there's got to be a trade-off somewhere, because I am the champion of Hornady manufacturing in, if somebody's building a rifle, I'm in their ear just nagging them, go shorter with the barrel, go shorter with the barrel, go shorter with the barrel.
Mm-hmm.
Ergonomics, suppressors for hunting specifically. I mean, my match rifle's got a 28-inch barrel. But for hunting guns, which we build often and we're always talking about, you strap a suppressor on that baby and it just changes the dynamic of hunting. Not to go on another tangent here, but I'm always in somebody's ear about, think about going 22, think about going 20, think about going 18. So there's got to be a gray area where you can get away with going shorter. Is that more realistically anything shorter than 18 or 16, or is it more powder charge dependent based, or both?
It's gonna be a largely cartridge dependent, cartridge, powder, bullet selection. But I think you're fairly safe 18 and over regardless.
Because I know several guys with 18-inch 300 PRCs that run the Thunder Beast Ultra 7 on those little suckers, and they just shoot great.
Yeah, and then if you go small calibers, 223, 6 arc, stuff like that, I mean, you can cut them back 14 and a half, 12
well,
inches.
Well, that's a good point. I'm glad you brought that up, because I know when you guys were doing the 6mm arc, you guys did a barrel chop down test, and you guys cut that baby down significantly shorter than 16.
Yeah,
and didn't see any accuracy degradation there.
Mm-hmm.
But again, that's a 30 grain powder charge.
Yeah, a lot of it is the ratio between the charge weight to bore volume.
Okay.
Or think of it charge weight to caliber for simple terms.
Mm-hmm.
So if you're, let's take like a 223. You're dealing with a charge weight that's somewhere in the mid to upper 20s, say 24 to 27 grains, and the 223 or 224, however you want to think about it. Take a 22-250. Same bore diameter, but now we're burning 40 grains of powder.
Yep.
If you cut those barrels back at the same iterations, you go from 24s and you start cutting back 2 inches at a time, you're going to see accuracy degrade faster at more soon at a shorter barrel length with the 22-250 than you are with the 223, because you have more powder to try to burn, and you need time to burn that.
Yep.
And there's just more of it there to go unburnt and have an effect on the bullet.
Yeah. And I was going to say it seems like it's you can think of it just kind of like you can think of the bullet entering the rifling. If it doesn't enter straight, it's going to enter crooked. It'll never fix itself, and it will never enter the same crookedness
Every
same
time, right?
And same thing with exit. If it exits and it's got all kinds of muzzle exit pressure kicking it in the butt, it's probably not going to do the same thing every time, and that's why you're going to get larger dispersion.
Mm-hmm.
But I think generally I've ran barrels as short as 16 inches on some, not large, but some medium caliber stuff. Shoots great. So for those out there that want to run a short barrel on a suppressor, 18 and longer for pretty much any small caliber hunting gun, you're probably going to be okay.
Yeah.
That's good, because it makes me feel better, because I'm all about that
and
life.
it's not a guarantee that you're going to have issues either.
Sure.
It's just you run the higher likelihood.
Yeah, there's more propensity for it.
Yeah, barrels have attitude. Some of them like it, some of them don't.
Yeah. The smaller the caliber with the more powder behind it, the more issues you're going to get with cutting the barrel back.
Okay, roger that. Awesome. So we started at you gingerly break the trigger, firing pin hits the primer, and we're all the way up now to that bullet right at the muzzle. Should we curb it right here, and then we'll do a whole other podcast on what happens the moment that that bullet uncorks, all the forces that are acting on that bullet that we have to encounter, and what is largely the study of external ballistics and getting your bullet out of the muzzle to the target.
Yeah.
Did we miss anything on the internal ballistic study? Or obviously we hit this on a pretty broad level. I mean, this is, having worked in this field for a brief period of time, you could spend a ton of time just, if we had a pressure velocity printout and just dissecting that. I mean, there's a lot that goes into it and a lot that you guys can learn from just looking at the curve. And obviously we barely brushed on propellant and some of the technology there and the chemistry of it. But I feel like we laid out a pretty good ground of what internal ballistics is, what we're up against from an internal ballistic standpoint, how we use some of this information. And you guys obviously do a great job of dumbing it down to my level.
I think there's one more thing I'd like to add, just as maybe an overall thing, especially for the reloader and the hand loader out there. Velocity is a function of pressure. So the reason you get the velocity that you get is because you generated enough pressure to cause that velocity.
There is no free velocity.
Barrel
length.
Barrel length. So that you're right. There's no free velocity, kind of asterisk, right?
Yeah.
So the caveat or the fine print to that would be barrel length. And the other fine print to that would be the progressivity of the powder that you were talking about or asking about earlier. Powders with higher energy contents, like our Super Performance line of ammunition, is a great example of that. And you can get on the website, you can kind of see some pressure curves that show what we're talking about. But essentially what happens is with Super Performance, we hit the same max pressure. It's not overpressure, it's the same max pressure, but that max pressure gets held for a longer duration of time, where the other ones, they hit max pressure and then it drops right off. With the progressive stuff, it hits max pressure and then it holds that for a little while and then it starts to drop off.
Okay.
And so that gives you free velocity because you're getting more at the same pressure. But from the perspective of the hand loader or the reloader, where you don't have a piezoelectronic transducer to measure your pressures and you're doing it off of stuff, maybe that's another thing we should talk about, stuff such as pressure signs, right? How does the primer look visually?
We're going to hit on that before we close this baby out, but okay, go ahead.
But the point is that that's your method to measure pressure. It's not a method to measure pressure. It's like an associative metric that can be true or false, depending on a whole bunch of things you can't control or measure. So just know, when your velocity is probably the best correlation that you have to pressure. So if I was a reloader or a hand loader, knowing what I know from my professional capacity, I would look at the primer and see what it looks like, and I would look at the back and look for ejector swipes and all those things that we're used to looking for. But the main thing I would hang my hat on is the velocity that it produced, because that will tell you if you're in trouble or not.
If you're in the real world,
if your ammo, if you're loading 6.5 Creedmoor 140 with a standard, applicable powder, H4350,
41.5 grains of H4350.
Let's go with that. We used to print it on the box, right? Yeah. If you're loading that powder with that cartridge and bullet combination, and you're getting velocities out of a 24-inch barrel, standard barrel length, that are 200 feet per second faster than SAMI recommends or Hornady publishes, you have pressure.
Yeah.
Like, you don't get that for free.
I don't care what your bracelet's
Hodgdon doesn't make mystery batches of H4350 that have unicorn poop in them that make them go 200 foot per second faster for free. It doesn't happen. So pay attention to your velocity.
I'd like to tack onto that in direct relation. Go to SAMI.org, pull up what cartridge you're shooting, what bullet weight, and if it's a crazy number versus what the standard SAMI spec is, then you probably have something with pressure.
Yeah, because that SAMI number has been agreed upon by all the professionals that are part of SAMI.
Members,
and that's us, that's Federal, that's Remington, that's the ammo guys, right? Like, that's what we do. And for those numbers to get approved and published in SAMI, everybody has to agree on them from a safety standpoint.
Yeah.
And so that's a really good, acid check.
Yep.
So I got two things on this. One, if you're getting traditional pressure signs, basically guarantees that you're exceeding the SAMI pressure, this 60 to 65,000 PSI range. If you have ejector swipes, now gas guns are a little different because there's some timing issue, but if we're talking bolt gun, if you're getting ejector swipes, ejector marks at all, you're over pressure.
Well over 65,000.
Yeah, that's usually a 70 70 to 75,000 psi
The
kind of
stuff
thing.
that I messed with when I was like way back in the day shooting 6-arc where we didn't have much data, I think I had like the second or third bolt gun, and I was just messing with different powders, and I would go till I saw a little ejector swipe, and then I'd back it off half grain, and then I got time to come out here and P&V them, and they were like 68, 70,000 pounds.
Yeah.
So that's not a reliable
And then
source.
primers are extremely subjective based on the
Yeah.
cup thickness, cup material. Like,
Aperture diameter.
Yeah.
There's
primer cratering is unreliable. You get some guns that have bigger firing pin holes than others, and it, So that's one point. If you see those pressure signs, if you have short brass life, that's a good sign that you're over 65,000 psi. And then what was my other point?
Hard bolt lift is another one to throw in
Oh
there.
yeah, hard
Yeah.
bolt lift guaranteed. You're in the 70s.
Or soft brass can do that
Yeah,
to you
soft
too. But
brass.
I mean, if you didn't do anything to your brass, like you're firing ammo and then you're going to reload that brass, and when it was fired as factory produced ammo, everything was fine, and then you reload it and you're getting bolt lift. I mean, that can definitely tell you you're high.
Yeah,
Okay. Yeah.
brass is never going to get softer as you keep firing.
So barring a manufacturing mess up on the brass side, which I'm not going to say never happens, but it's pretty uncommon.
Yeah.
And then so my other point was our handbook data is not lawyer loaded.
No.
When there's no lawyer watching the lab tech, checking him off like, oh no, you better back that one down. Like what we post is what a lab tech got for SAMI max pressure in that cartridge.
Mhm.
And that's the charge weight that we put in the book.
Yeah, that's a great point. Yeah, that's not. Yeah, I've heard that a lot back when I was in technical service answering the phone. Is someone would refer to those as lawyer loads, and then now I'm the editor of that handbook, and I work really closely with the lab, and as they develop the data, and the data is ran up to SAMI max pressure, and that red line load is SAMI max and should be approached with caution.
Yep.
Caution, excuse me. Great point. So I'm glad we went down this rabbit hole quickly because we've all been there where somebody has said, well, I'm loading fill-in powder, charge weight, getting this much velocity with no signs of pressure, but my brass only lasts 2 or 3 firings. It's like that's the sign of pressure that you're talking about.
Yeah.
And I'm also glad you brought up the point, and I was going to bring it up if you didn't, Jacob, because I know you did this testing where you worked up loads. I know you did it in 223 as well as 6-arc, where you saw quote-unquote traditional signs of pressure at either a sticky bolt lift, ejector stamp, or swipe or whatever, and then you would go test those in the best pressure reading system on the face of the planet, and you could say, okay, I saw these pressure signs, and where most people think it's 65 or whatever, it's happening. You don't see those until you're 68, 70,000 pounds.
Yeah.
And then when you're building stuff on custom actions where all these tolerances are so tight and all the mating surfaces are just perfect, you don't see those until you're in excess of 70,000 pounds
You're
of pressure.
10 to 20%.
I was going to
over what
mention
you're
that
supposed
if
to
you
be.
didn't, the custom actions and even the mass manufactured factory actions today are so much better tolerance wise that those traditional signs, they maybe had some validity to them when your firing pinhole was huge and all that, all the other variances in your actions. But now actions are held to such tight tolerances that those are not really relevant. Relevant gauges to use today.
Yeah. Like I said, it guarantees that you need to back down.
Yeah.
Yep.
I think those pressure measurement methods are valuable if you have no chronograph to measure velocity, which you know most of the history of reloading is that circumstance. Until recently, we can buy a personal chronograph or lab radar or whatever you're going to use magneto to measure velocity, whatever it is. But we don't really have that excuse anymore. If you have a velocity measurement tool, use that. Still look for the pressure sign stuff because that old method is not something to just throw out. It might warn you of something like Miles talked about. Like if you're getting those signs, you're likely over. But start with that velocity, because as recommended, you should start at a middle grain, charge weight, and then work your way up looking for signs of pressure. Well, check the velocities as you're doing that, and if you reach that point where you're getting velocities that are agreed upon by all the professionals, at SAMI or whatever it may be, if you want to keep going, that's on you.
Yeah.
You can no longer complain about leaking primers, pierced primers, shortened brass life, shortened case life before you start getting cracks due to lack of annealing or any of those associated things. Like because you knew you were at pressure because you were getting standard velocity and you kept going. So that's on you.
Yeah. Velocity is not free.
Yeah.
That's a great way to put it. And we've all heard it. And I'm glad, like I said, that we went down this route, because there's a lot of myths. There's a lot of old school thinking. There's a lot of just, this is the way it is because I was told this is the way it is, and all that information out there on the internet. And it's good to hear it from you guys that, velocity is not free.
It's nice working for a place that gives us a little bit of freedom to go after those myths, see if it's true, see if it's BS, and test it out.
There's been a time or two I've seen stuff on the internet and been like, I wonder, and I go pressure test it, and I've seen as high as 83,000 psi.
Wow.
From stuff that people are posting on the internet. Oh, I have no problems. And it's like, yet.
Till you do.
Yeah.
Till that bolt lugs let go, or
hope you keep your face.
That's scary stuff. Awesome. Well, this has been an incredibly educational time for me, and I'm hoping our listeners really digest this well, because again, it's just a field of study that not many people have the ability to learn about. And we're all lucky to be able to work here, but all of us normal employees are really lucky to work with guys like you that are in this field, that are in the weeds of internal and external ballistics. So let's wrap this up on the internal ballistic study side, and let's carve out a time here in the near future to talk about what happens when that bullet's uncorked and all of the things that we're fighting against that basically want to stop that bullet from getting to where we want it to go. And from there, we're going to have to really dive into ballistic coefficient and what that is and how it was formed and what its deficiencies are. And then we can talk about drag coefficient and CD versus Mach curves, and eventually get into Fordhoff. And this study of ballistics is just awesome, and I'm excited about it. And hopefully our listeners are just as excited to get some good information out there about the study of ballistics. So thank you guys for coming on.
Yep,
Absolutely.
Awesome. Everybody, hopefully you enjoyed this one. I know I did, and we will catch you guys on the next one.